Welcome to the part 2 of your previous lecture, Study of Chemical Reactions. To understand what is entropy, look at the reaction. Nitrogen pentoxide is an unstable solid that undergoes a spontaneous and endothermic decomposition to nitrogen dioxide and oxygen. Clearly, some factor other than a change in enthalpy must act to favor this decomposition. If we balance the equation, 2N2O5 is equal to 4NO2 plus O2. So here two well-defined molecules in the solid state break apart into 5 discrete product molecules, all of them in gaseous state. This thermodynamic name for this tendency towards randomness or disorder is entropy. Symbol S. Entropy increases spontaneously since greater randomness or disorder in a system has a higher statistical probability. Since the disorder created by molecular motion increases with temperature, the units of entropy, EU, are calories per degree Kelvin per mole. Only differences in entropy have significance. So the standard state entropy of a substance is the difference between its entropy at 298 degree Kelvin and its entropy at absolute zero, defined as zero by the third law of thermodynamics. Two obvious trends to note are that gases have higher entropies than liquids or solids of the same size, and molecules composed of many atoms have higher entropies than diatomic or triatomic molecules. The entropy change in a physical or chemical transformation is written as delta S and defined as S products minus S reactants. This is the same notation used to represent an enthalpy change, and the sign of delta S indicates a similar directional change. Thus, a positive delta S denotes an increase in entropy on going from reactants to products, while a negative sign is associated with a decrease in entropy. Here are some points to remember. For a given number of total atoms, a process that converts a few large molecules to many smaller molecules proceeds with a significant increase in entropy, that is delta S0 is positive. If the total number of molecules remains unchanged, a process that converts a single molecular species to a mixture of different molecules proceeds with a significant increase in entropy, that is delta S0 is positive. In general, a change from a condensed phase, that is from liquid or solid, to a gaseous state will proceed with a significant increase in entropy, that is delta S0 is positive. Ionization reactions in solution are complicated by solvation effects. The expected increase in entropy from the first factor listed above here may be offset by solvent molecule orientation about the ions. This ordering of solvent molecules causes a decrease in delta S0. Now our next topic is free energy. What is free energy? The interaction between enthalpy and entropy changes in chemical reactions is best observed by studying their influence on equilibrium constants of reversible reactions. To this end, a new thermodynamic function called free energy or Gibbs free energy, symbol delta G, is defined as shown in the first equation below. Delta G0 is equal to delta H0 minus T into delta S0. Delta H is enthalpy and delta S is equal to entropy. Here, two things should be apparent from this equation. First, in cases where the entropy change is small, delta G is nearly equal to delta H. Second, the importance of delta S is in determining delta G increases with increasing temperature. A second equation shown below is important because it demonstrates the fundamental relationship of delta G0 to the equilibrium constant K. That is, delta G0 is equal to minus RT ln K or is equal to minus 2.303 RT log K. Now, the free energy function provides improved insight into the thermodynamic driving forces that influence reactions. A negative delta G0 is characteristics of an exergonic reaction, one which is thermodynamically favorable and often spontaneous. Likewise, a positive delta G0 is characteristic of an endergonic reaction, one which requires an input of energy from the surrounding. Now, the point listed the thermodynamic requirement of any reactions. Because of the negative logarithmic relationship between these variables, a negative delta G0 generates a K greater than 1, that is, equilibrium favors towards products, whereas a positive delta G0 generates a K less than 1, that is, equilibrium favor towards starting materials. When delta G0 is equal to 0, that is, K is equal to 1, indicates 50% conversion of starting materials to products. Furthermore, small changes in delta G0 produce large changes in K. Now, kinetic requirement of reactions. What is kinetic requirement? Value of delta G0 indicates how far a reaction goes to completion under a given set of conditions. But how fast the starting materials are converted to products is also needed for proper assessment of the reaction. You have seen from this graph that this portion indicates energy barrier, delta G star, and this portion indicates thermodynamic requirement, but this portion indicates kinetic requirement. To account for the solution of undergoing a chemical reaction, two theories have been proposed: collision theory and transition state theory. In our next episode, we will discuss about them in details. Thank you.